Yeah, so hello everybody. Welcome to the second actual example of using Jupyter notebooks. In the last couple of videos, we actually talked about model-free prediction and we found two different algorithms. The first one was Monte Carlo learning and the second one was time difference learning. And in this video, we actually want to dig into the Python implementation of a time difference learning example. We will use the same environment that we also did in the first video. We have a FrozenLake 4x4 grid world with stochastic actions, probability transitions. As in the last video, I will turn off the video in order to not distract you with my face. In order to get started, what we first need to do, we need to activate our environment. This is actually also what we did the last time. You can take the same dependencies. We will start a Jupyter notebook. On the download, you will find the TD FrozenLake example. You can start them as before, as we also did it. And what you will find here is the TD agent in our FrozenLake environment. This now is not so important. Today we'll really focus on the time difference learning agent. Yeah, so what do you find here actually? You will find, as in the previous example, you will find a short description of the MDP. In this case, today we will not rely actually on this implementation. We will really use the problem that is provided by the gym environment. You will also have the OpenAI gym introduction you had in the beginning. And now we really use the example from the gym environment because we now do not have or need the access to the probability transition matrix, and we really can actually perform in the model-free environment. Yeah, so the task is actually given as the same. So the task is the same one, and we have a non-deterministic transition model. Yeah, so TD learning, as we have described it in the lecture videos. We have this bootstrapping update function, and we update our value function according to a guess of our previous value of the state. Yeah, so but now let's get to the real content. How is actually the TD agent is implemented? Yeah, so this is our implementation of the TD agent. You will see lots of similarities actually to the dynamic programming agent. Our agent just is initialized with a discount factor and the learning rate, both of which you actually have learned in the lecture about, and the agent initializes its MDP. We set the terminal states. The terminal states are actually also the same as in the dynamic programming environment and also in the OpenAI gym environment. We initialize our value function estimate with zeros, and this is actually the implementation of our policy. So what our agent currently uses as a policy is just a random policy. So there's actually 4 different actions, left, down, right, up, encoded with 0, 1, 2, and 3. And what we do is we just sample a random uniform value between 0 and 1. And depending on the value, actually we select depending on the returned value between 0 and 1, drawn from a uniform distribution, we actually calculate our action. In this case, every action is selected based on the 25% chance of being there. And what you see here is, in contrast to the dynamic programming example, this is the actual TD learning update function. And you see it's, I think it couldn't be any easier. You just say that for any transition that you actually obtain, state, action, reward, and next state, what you do is you update your value function estimate to a value, to the current value plus the learning rate times the reward, the discounted return minus your previous estimation. So yeah, so in a one-liner you actually can define TD learning and you can put it together with your policy, and this already defines your complete agent. So what we do now is we just execute this declaration. So actually now our TD agent is actually defined. Now we can initialize our agent. We just say that we have a TD agent that uses a discount factor of 0.95 and a learning rate of 0.1. And we use a gym FrozenLake V0 environment. And now what we do is, now we do not perform sweeps over the whole state space as we did in the value iteration example where we actually use 20 iterations. What we now do is we perform 10,000 steps actually through the environment. And what we now need to do, we have actually need to make use of the OpenAI Gym interface. What we do in the beginning, actually, we reset the state and the environment. So actually our first state and observation is obtained by just calling the reset function on the environment, which actually sets, in this case, the agent to the start position. Yeah, so, and then we iterate like forever, actually. And what we do is we use our TD agent, actually the policy implemented in the TD agent, to give us an action based on the state we are currently in. So in this case, this is the random policy. You can feel free to update the policy as you like. You can also evaluate different policies. Then we obtain the next state, the reward, if we are done or not, and the info flag if upon stepping through the environment. So actually we call the step function using the given action on our current environment to obtain the next state. So, and now we already have the first example experience that we can use to actually update our time difference learning agent. In this case, we use the update function and call it on the agent TD, and we provide him with the state action, the reward, and the next state. This is actually what the update function here wants to have. Yeah, so that's it. At the next point, we just reset the state we are into, so that we can actually select the next state. When we go into the next iteration, we just update the state. And what we need to do is we need to define if our episode is actually terminated or not. Yes, and in this case, what we just need to do is we just need to look at the dump flag. If it's true, then the episode ended. If it's not true, we just can keep going. I just did something wrong in the beginning. This actually is the number of episodes we want to run through the environment. It's not the step size, not the steps through the environment, because the environment actually all the episodes are running in here, and we just go out of the while loop as soon as actually the episode ended. So yeah, value function is calculated. Now we want to let our agent visualize our value function, and we just do this by this one. And what you see here is that, it's our value function. You see for each of our states, the actual calculation of the value function. Most of the holes are 0, and also the goal is 0. And what you see is like the evaluated value function using a random policy. Yeah, so what do we know about it? So actually we know that this one has the highest states. And maybe let's just play around a little bit with this agent and the TD learning example. What could we do actually, or how could we actually improve our policy to actually increase this value? To check and to see if the algorithm is working. So what would actually happen if we would increase the probability of going to the right? What you see now is that the agent does not really depend on the state. So actually the state is provided to the agent, but the selection of the agent does not really depend on it. Let's just leave it like this. Just let us increase the value of of taking action right, which actually is just defined by increasing the bin size actually for this number to let us select A. So now we have a 35% chance of actually taking action right. So what would change? So if we now rerun everything, rerun our agent, would we see an increase in this value in here? Probably we see, probably we don't. Yeah, so probably we don't. Why is this the case? There's two reasons behind it. Maybe think about it for a short minute. But the case is that we draw random samples, both from the environment and also we draw random samples to select our actions. While these two are very narrow and should level out, we really have also hyperparameters that let us really lead to different results. So what we use the learning rate of 0.1, which is considerably high, which is maybe a larger, which is basically a value that introduces too much noise and variation in the environment. So now let's change this. Maybe let's go back to actually go a little bit towards, so we actually want to maybe even further decrease the learning rate, but then in turn let's also increase the experience samples that we collect. And what we now do is restart and clear output. Let's rerun this to get a proper estimation of the value function. We rerun every one of our, now takes a little more time, but I hope it should like end quickly too. It's also it keeps running. Yeah, it's now done. And let's now actually visualize our value function. So now what you see is our value function for the state below here is 0.4293. So now if we now want to increase the value of going right in this case, what would happen? So maybe we should really take our time and remember the value function. So in this case, it's it's about 43% chance of going to the right. And although we might get a different result, what you now see is that the value really increases a little bit. This might also jiggle a little bit around, so let's run it again. Oh, sorry, I need to run this again. Oh, sorry, I would have needed to run this again. But what you will see that you will get close to this values, or if you really apply the new policy. And if you really go with larger learning rates, actually you get much more variation in this value. But this is actually where the stochasticity comes from. And this is a hyperparameter you also need to tune in TD learning, which you would not really have to do in dynamic programming, as there was no experience sampling and nothing really that makes an influence on this. Yeah, so feel free to play around with this one, add things, and yeah, have fun with this implementation. Bye.